Hello and welcome to Minds of Pint Einstein, the science show. My name is Marcus Chown. I'm a science writer. I'm the author of books like Quantum Theory Cannot Hurt You, The Ascent of Gravity, and my latest, which is called, what's it called? The Magicians. And it's my great pleasure today to have with me the man behind the James Webb Space Telescope. Now, I met John Mather many years ago, I can't tell you how many years ago, when I wrote my first popular science book. And I went to America and I interviewed him at the Goddard Space Flight Center, which is very close to Washington, D.C. And at the time, I had no idea that he was going to win a Nobel Prize. And I didn't realize that he was going to be the project scientist of the successor to the Hubble Space Telescope, which is the James Webb. So welcome to the program, John. Thanks very much for having, for sparing us your time. Can you hear me? Yeah. Oh, fantastic. I see you now. So really, what we hope to do is look at some images, and maybe you can talk us through what those images show. But really, to start with, I just want to say, how's it going? I mean, has it exceeded expectations, the telescope?
Oh my goodness, it's far better than we hoped it would be. And the universe is far more beautiful than we ever hoped it would be either. So the pictures are fantastic. The telescope is working perfectly. So we are beyond ecstatic. We are thrilled.
You must be relieved as well.
Yeah, we're relieved, yes, because there are so many ways you can imagine that bad things could happen to you, and they mostly didn't.
So can you describe for our listeners the telescope, where it is, how big it is, what instruments it has? I'll put it up on the screen as well while we're talking.
There we go. So it's 1 million miles away from us, 1.5 million kilometers, orbiting around a place we call Lagrange point 2, which is in the opposite direction from the sun. So it's overhead at midnight. It has about half the mass of the Hubble Space Telescope, but the mirror collects 7 times as much light. So this is an incredible achievement of engineering to be able to fold up a telescope that big and get it into the top of the rocket and get it so far away from Earth. So the great mirror that we have is made out of 18 smaller mirrors that are all coated with gold. So why do we coat it with gold? So it reflects the infrared light that we're after much better than other kinds of metals would do. It is cooled down to an extremely low temperature, so it does not emit its own infrared light. And we launched it on Christmas morning last year. So just almost a year ago exactly from today. So
and these segments, I mean, they're hexagonal segments. Did you say there are 18 of them?
Yeah, 18 segments.
And they're gold because they reflect infrared. This telescope doesn't see light that is visible to the naked eye, but heat radiation. Is that right?
Well, mostly. It can see orange and red, but it can't see blue. So it's not a replacement for the Great Hubble Telescope, which can see shorter wavelengths, even ultraviolet wavelengths. And on the other hand, the Hubble cannot see what the Webb can see.
Yeah, and to keep the detectors, the infrared detectors, cool, that's why you put it at the Lagrange 2 point, is it? A long way away from the Earth. And it's got a huge, great sun shield, hasn't it?
Yes, that big umbrella has 5 layers of metallized plastic, and it's as big as a tennis court.
And so the telescope is in its shadow, and that keeps it basically at the cold of space. So you get your refrigeration for free.
Yes, we refrigerate the telescope and the instrument package for free, but we do have one instrument which was actually assembled and tested in the UK and the lead person in the UK was at a Royal Observatory in Edinburgh, Gillian Wright. So she did a marvelous job, and it was the first instrument to be completed and delivered to NASA. So we're thrilled with it. Anyway, that instrument needs to run at 7 degrees Kelvin, 7 degrees above absolute zero. So it needs its own very special refrigerator, and it works.
Right. Wow. And the reason for using infrared is because we want to look a long way away and because light has taken a long time to get to us. We're looking at the early universe when the universe was smaller, And in that time, since the light was emitted, the universe has expanded and stretched the wavelength of that light out of the visible to the infrared. Is that right?
Yes, that's right. The wavelengths have stretched out. What used to be visible or even ultraviolet is now infrared. So this is the telescope to pick up light that was emitted by hot stars when they were very young. And now it's long wavelength. We have other reasons also to observe the infrared. Things nearby us that are too cool to emit visible light still emit infrared. You're emitting about 500 watts of infrared power right now. You don't notice it, but you are. And also, we are able to see through dusty clouds of gas in space. Dust grains stop visible light, but they don't always stop infrared. So the longer the wavelength that we use, the better we can see through the dust clouds. So that's one of the reasons some of our pictures are so very different from what we had with Hubble.
Now, you've been in charge for 26 years, I think. Can you
Yeah.
tell me about the high points and the low points of that long journey?
Oh my goodness. Well, the high point was being invited to work on the project. That was October of 1995. And so a little book had been written calling for this telescope to exist. A committee wrote a wonderful report, and when I saw it, I said, oh, this is the most important thing I could possibly be working on. Of course, I want to work on this project. So then I got to be participant in the initial stages of creation of what the telescope would look like, making out a list of all the things we would need to invent so we could have the telescope. Then, of course, we worked and worked and worked and worked and worked. We had a few moments when it was seemed like we wouldn't have enough time or money to finish the project. So I wasn't scared, but I was very glad that we were rescued by people who knew how important it was. Politicians in the United States and in Europe and Canada all stepped up and said, okay, yes, we think this is really important. We will still work with you, even though it takes more time and more money. So that was a little bit scary, but not that scary. Personally, it's a little bit scary to watch your telescope sitting on the shaker. We have to shake the telescope to see if it will survive launch. And of course, it always does, but it's still scary. Then, of course, there was the great moment of launch. Here and almost everywhere, people watched it from home because COVID was very popular, should we say, in those days. And so we were afraid of getting it to transmitting it to the people who had to run the observatory. So everybody stayed home. I did too. And then, of course, it worked beautifully.
Didn't you have a problem with a hurricane or something at one point?
Say that again?
Did you have a problem with a hurricane or something at one point?
Oh, yes, we did. We had our telescope was in the vacuum tank in Houston, Texas, at the time when Hurricane Harvey rained down with about 48 inches of rain, over a meter on the telescope building. But none of it, of course, got into the vacuum tank. Our people had to be very creative and very heroic to survive that and to save the telescope from certain hazards that occurred in the middle of the hurricane.
I mean, 26 years, our understanding of the universe has dramatically changed in 26 years. I mean, for instance, we now know that the major mass component of the universe is something we completely overlook, which is this dark energy that, I don't know, accounts for something like 70% of the mass energy in the universe. So did you have to change the design of the telescope as the astronomy and our knowledge changed?
Well, no, actually. We did have to adjust our thinking about what we would likely see. We did have a couple of changes that we made. One was we had to shrink the telescope a little bit because we realized we couldn't afford the design that we had. We were asking for an 8-meter diameter telescope. And eventually we realized we couldn't afford the time or the money, and it probably wouldn't fit the rocket either. And so when you see the design that we have, well, it just barely fits. So we did the right thing.
So the reason it's segmented is because you couldn't fit it in the nose cone of the Ariane rocket. It had to fold up.
Right. It's much bigger than the rocket, especially that sunshade. So even when we get even bigger rockets in the future, it'll still have to be folded up if we want a telescope like this.
Right. So I mean, and then of course you put a bomb under it, and I understand there were like were there 344 things you had to get right,
Yes,
any one of which could have scuppered the entire project.
yes, we call them single point failure locations. And so we, of course, gave them extreme attention. This is mostly about unfolding the telescope and the sunshade.
Yep.
It's like packing a parachute. You know how to do it, and you have to do it right every time. So that's our job, is to do it right every time. And so that's pretty scary in an abstract sense. But the critical thing is you make sure that everybody that's working on the project knows how to do their job, and you make sure that they actually do it.
How did you stand the stress, not only of the 26 years, but the stress from the launch to actually it functioning?
Yeah, I did not feel much stress about that. I knew that we had done the right thing as near as we could
Right.
possibly manage. Our funds had been sufficient to carry out all the tests we thought were necessary. Our team is incredibly talented and dedicated, and they did everything that they thought was necessary and I thought was necessary. So what more can you do? You've done everything you can, so might as
Yeah.
well enjoy the launch. And
I'm
so I
just
was not
thinking that
worried.
obviously, yeah, sorry, I'm just thinking that in the back of your mind was there the fact that Hubble was launched with a squint, but because of an error.
Yes, of course, that was the number one question we addressed with the concept. How are you going to make sure that doesn't happen to us? So, of course, several things. One is design it so that can't be. Number two, test it so you're sure. And
Yeah.
number three, have really smart people argue with you. We call it review.
Mhm.
And so if you passed all three, then there's a chance that it'll
Right.
work.
Wow. And obviously when things went wrong with Hubble, it was possible to mount a space shuttle mission and give it basically a correcting spectacles or whatever. But of course you can't do that with yours. It has to work.
No, we can't. It's all stuck together and it's not made for being fixed. By the way, future missions probably will be made so they can be fixed because now we have the technology to reach way out there with rockets, and astronauts can even go there soon. So it's going to be possible in the future, so we could fix them.
So is it going to be limited by things going wrong that you won't be able to fix, or what will limit its lifetime?
Okay, the lifetime that we know about is limited by the fuel. We have some rocket fuel on board, which we use to make sure the orbit stays correct. And also, although you might not feel it, the sunshine pushes on that great sunshade and tries to turn the telescope over. So we manage that pretty well, but once in a while we have to fire the jets.
Right. And are you getting micrometeorites that are hitting
Yes,
the surface
yes.
of the mirror?
Yeah, we have about one a month, little tiny sand grains that hit the mirror. They're about 1,000th of an inch across. So very, very tiny, but they come very fast. So if one hit you, you would feel it. But if you had one in your fingers, you would not. So
Right.
they're so tiny, but so fast. So we had one that hit a vulnerable spot and made a noticeable bump on the mirror. And so far, we've only had one. The others only make tiny pits that really don't matter to us. So we haven't yet fully understood the engineering possibilities of how we have a vulnerable spot. But anyway, we're pleased we've only got one. And
So
at the rate we're
how would
at, we'll be fine even for 10 or 20 years of mission life.
wow. And how do you go about using the telescope? What do astronomers do? Is they put in a proposal. There's a team
Yeah,
that judges it.
yeah. Every year we ask for astronomers to send proposals, and a new batch is due in January. And so people around the world send us proposals. We tell them how to write them and what they have to tell us. And by the way, we tell the people, do not tell us who you are. We want to be able to read these proposals without prejudice about thinking, well, so-and-so is really smart or so-and-so is not. We wanted to get the proposals that have the best ideas. So one of the results of that is young people succeed. about 10% of the last round of proposals were submitted by graduate students. So these are people that were just being born when I was starting the project. And so this is super. We were so pleased with this.
I mean, tell me about the first image. Can you remember when the first image came through? What was it, and what did you think? What did you feel?
Yeah, well, the first one that we saw was when the engineering images, when the telescope was in focus. And we had a special day when everybody expected to see this image for the first time. And so engineers and scientists were there in the control room. And it was breathtaking because not only was the telescope in focus, but there were galaxies everywhere in the picture. So this is something we really hadn't appreciated, that the telescope is so powerful that no matter what you do, there's a galaxy in the picture.
Is this the image that I've just put up?
No, this is the first one we released to the public as a science picture.
Right.
So this is the one that President Biden announced on July 11th. So it's fantastic too, and it's even more fantastic in its own way because of what it has in it.
So this was the telescope looking at a completely blank, dark piece of sky.
Well, not quite completely dark, because you can see there's a few bright fuzzballs there in the middle, which turn out to be enormously massive galaxies, pretty close by. And then there's a lot of funny looking little reddish arcs in the picture, which turn out to be very, very distant galaxies that had been magnified and distorted by the gravitational force on the light as it goes by the nearby galaxies. So Einstein gave us some extra lenses in the sky that we now use on purpose. I can't say Einstein did it, but he predicted it.
So you've used your telescope plus nature's telescope in this picture to see even further away.
Absolutely. And so this technique is clearly proven in this picture. Sometimes you see a galaxy twice or even 4 times in one picture. And sometimes we say, well, the magnification is really high, like 10 or even 100 times in some places. We have some places where the gravitational lens has a magnification of over 1,000. So that means you can see individual stars at immense distances. Something we could hope for, but we never could really imagine.
So this is the equivalent of the Hubble Deep Field. I remember that the Hubble looked at a very, very tiny portion of dark sky for, I can't remember, it was maybe 12 or 13 hours. And to everyone's surprise, it turned out to be filled with galaxies, at enormous distances. So this is how many hours did this exposure take?
I don't remember exactly, but it's a few hours, like 2 or 3. And so in a few hours, we can already see better than Hubble could see in a few weeks.
Right. So this just really shows you the potential of the telescope. So are there galaxies in here which are the furthest that human beings have ever seen them, or the furthest back in time that we've ever seen a galaxy?
I think we may have some other places where there are even more distant ones that people are working on right now. But right away in this picture, we saw galaxies that were formed within about 300 or 400 million years of the expansion. So we see them as they were when they were very young. Of course, the light that we receive from them is very old because it's been traveling all these many billions of years. So you don't really recognize them in this picture because what they actually look like is tiny red dots. So you don't know that they're interesting until you find out what they really are. So to find out what they really are, you first have to identify them by their color, like they're super red. And then you have to get a spectrum of each one to say, well, what exactly is in them? What wavelengths are we getting from particular molecules or atoms like hydrogen and oxygen? And if you see the pattern that you recognize, you say, I know how fast this object is moving away from us, and I know what's in it. And so that's how we tell when we found the most distant galaxies. They're moving away from it as fast as possible.
You attach a redshift to the galaxy. I mean, what are the redshifts of these very distant galaxies?
Yeah, we have redshifts now are being reported up to 16 or so.
So the universe was about 16 to 17 times smaller in dimensions. when that
Yeah,
galaxy emitted its light.
right. One clarification, though, when we say the universe here, we meaning the piece of the universe that we can see.
Yeah, yeah.
Um,
So
People are often about this.
things were 16 or 17 times closer together than
Yeah,
they are in today's universe.
right. So the whole
And
universe that people ask about is probably infinite. That is to
yeah,
say, it wasn't infinite when it was young and is still infinite, which means going on beyond limit. We just can't see that far.
and I mean, this is incredible that we're seeing within a few 100 million years of the Big Bang, because I mean, that's only maybe a percent or something or less of the age of the universe. And
Yeah.
we're already seeing galaxies. I mean, things that are recognizable as galaxies that early. Is that a surprise?
Yes, it is. We expected to find them, of course, but what we are surprised about is they're brighter and more organized than we imagined. When we had pictures previously, they looked kind of irregular, and now I think what we're seeing is that actually we're typical of modern galaxies, just smaller and a lot brighter.
And does that pose any problems for ideas of galaxy formation?
Well, I think it just tells us how hard it is to figure things out in advance.
Yeah.
That we have calculations. We have many wonderful computer simulations and wonderful movies of how we imagine stuff works in those early days. And we should not be surprised if they're not right.
So
Because there's
are we hoping to see the very, very first galaxies, the very, very first stars? That's really one of the aims of James Webb, is it?
It certainly is, although knowing when you've seen one is actually tricky.
Mm.
If you saw a little red dot, you'd say, what is that? Then you spread out the light into the wavelengths and you say, well, it's got the emissions of hydrogen and oxygen and a few other things maybe. And you say, well, that can't really be primordial because the beginning had only hydrogen and helium, no oxygen. So one of our jobs is to find the little tiny red specks that have no oxygen in them. And then maybe we have an idea that we've seen some of the very, very first galaxies.
So
they're hard to find.
The universe was born in the fireball of the Big Bang, but that faded. It basically was no longer optical, and it faded, and we had this dark age which went on when the universe doubled in size, and it doubled and it kept doubling, with incomplete darkness, but with matter congealing under gravity, and then suddenly stars switched on all over the universe like lights on a Christmas tree. Is that what happened?
Yeah, that's a pretty good way of saying it. We measured cosmic microwave background radiation, and that's a map of what the universe was like when it was about 400,000 years old. So it had hot and cold spots that correspond to density variations, and we imagined that the most dense regions have enough gravity in them to stop themselves from expanding and turn around and collapse back down into something. And so what is the something? Did they make stars directly? Did they make galaxies that then made stars inside them? Did they make black holes first? This is one of the great questions that's still wide open for this telescope.
Yeah, I mean, Hubble famously discovered that there was a supermassive black hole in the heart of every galaxy, and by not knowing that, we were missing a major ingredient in the recipe for making galaxies.
Yeah.
But we still don't know that those supermassive black holes formed remarkably early, and we don't really know how. Do you think we might get any clues to how they formed so early?
Yeah, we are. We're beginning to understand the connection between the mass of the black hole and the mass of the galaxy. These days, we find that the mass of a black hole is typically a few percent of the mass of something they call the bulge, the portion of the galaxy. And we just don't know why that is, even after all these years. So we're looking back in time and we're seeing it maybe isn't always the same ratio. So maybe the early galaxies formed in a completely different way. Which formed first? Did the galaxy form first and then make a black hole, or the other way around?
Yeah, no. So interesting stuff. Let's have a look at another image, if I can show. So this image shows you, I think is it the Eagle Nebula? Is that
Yeah,
the Eagle?
this is the picture people.
The left-hand side was taken by Hubble, and the right-hand
Mhm.
side was taken by James Webb.
Yeah, so there's a big difference. On the left-hand side, you see those wonderful dust clouds we were talking about that are opaque for the visible light that the Hubble can pick up. On the right-hand side, you see the clouds are much more transparent, and you can even see really bright spots where new stars are burning themselves. They're really bright and they're lighting up everything. And anyway, that's part of the excitement of this picture. Is it shows how new stars are being born inside those clouds. So once in a while, you can find one that's particularly interesting, and that you understand.
That in those images, the detail is roughly the same, even though the James Webb is bigger because it's using a larger wavelength.
Yes.
It sees blurrier images, but they kind of match, don't they?
Yeah, they match very well. The Webb telescope actually has somewhat sharper pictures than Hubble, just because it is bigger when we're working at the same wavelength.
And these what we're seeing here is, I mean, you were saying that the dust is opaque to visible light, but not to the infrared, so the James Webb image is so much clearer. But what we're seeing is a stellar nursery, aren't we? And
Yes.
I think that these are not pillars. I think they're called the pillars of creation. They're actually windsocks, aren't they? That the newborn stars are above the top of this picture, and their stellar winds are blowing away this dust, which is
Yes,
where the stars are forming.
Yeah, that's really a good analogy because it really is. There's sort of rocks in a stream. The wind is blowing by at immense speeds. Also, the heat from the new stars that are just above the picture is so intense that it's sort of evaporating the surface of these clouds. So you see in the right-hand picture how there's a sort of a yellow region in the middle, which is being lit up by nearby stars and made hot. So that's one of the reasons it's so interesting for astronomers. We can see the physical processes happening right in front of us.
And at the tips of these pillars are the newborn stars, and all the dust is being blown away. Some of them presumably won't even form stars because the dust will be blown away before it can condense.
Yeah. By the way, we should say, why is a dust cloud the place where stars grow? And the reason is that in order for gravity to overcome the force of gas pressure, the gas has to cool down. So how can the gas cool down? Well, if it's protected by dust from the heat of the nearby stars, then it can cool down. So the exact reason why it's hard to study is the reason that it exists. So
Yes.
This is why we're looking at these places. There's a real good reason for this to be the place where stars are born.
And one of the ways that stars or forming stars lose their heat is by molecules emitting microwave radiation, carbon monoxide, molecular hydrogen, that kind of stuff. And that cools down the interior of the cloud so that they can actually collapse under gravity. But that mechanism was not present for the first stars, was it?
That's right. The only molecules that existed in those days were hydrogen 2, the same kind of hydrogen molecule that we have here. So it's not very good at cooling off dust clouds or clouds that don't even have any dust. So that's one of the reasons we think the first generations of stars were very different from the ones that we have today. And we seem to be verifying that prediction. The prediction says first stars were maybe 100 times as massive as the sun, and they would burn out in about 3 million years. So much brighter, much hotter, and burn through the fuel really fast. So
and they would leave behind very large black holes, presumably.
Yeah, something happened anyway. Somewhere the black holes grew. So it is calculated that some of those very massive stars could turn directly into a black hole. So we even saw fairly recently, close by, one of them did it. The star just disappeared.
So the actual gas cloud could actually turn into a black hole before forming a star that then collapses to form a black hole.
Yeah, there's multi-step process. First, you make the star, then the star burns out, then the star collapses into a black hole. That's one thing that can happen.
Okay, let's look at some of these other pictures if I can. So that's that same is the Eagle Nebula again, and showing even more detail, isn't it? Really, that one.
Yes. So they've given us longer wavelength sensitivity in this picture to emphasize the cooler regions and make it more transparent so we can see through better. And so we actually have the capability, although I don't know if we did it in this picture, to identify the radiation that comes from particular atoms or particular molecules. So we can make a map of chemistry through a cloud like this. And you see, for instance, on the right-hand side in the middle, there's a really bright red dot. So that's obviously one of the brand new stars in there.
And this would have been, our own sun would have been born in a dusty gas cloud like this 4.5 billion years ago.
Yeah, that's what we think.
This.
And by the way, we are getting evidence in some places, like the Orion Nebula, where we can actually see a disk of material orbiting around a new star, presumably forming planets as it does it. So new solar systems being born as we speak.
Yeah. So do most stars have such a disk, or 10% of stars? Do we know how many have planetary systems?
Approximately 100% of stars have planets. So they must have done it through this disk process. So we should always expect that it's there. We can't always see it.
I suppose one of the things that we've discovered while your telescope has been under construction is that all the other solar systems around other stars, none of them are like ours. We seem to we like to find that we are, we are an average, normal type of whatever. But actually, we found that our solar system appears to be extremely unusual.
Yeah, which is a little surprising because the revolution that Galileo started says, well, we're not special and different. But maybe we are in some random way. Nobody quite understands why there aren't more solar systems that look like ours.
We appear to be missing
lots of solar systems, but
we appear to be missing a type of planet that nearly every other solar system has, which is like a giant water world or a small Neptune type planet. We seem to be missing those, don't we?
Yeah. So what we have that's special and different is we have 4 little rocky planets in the middle: Mercury, Venus, Earth, and Mars. Then we have a gap where the asteroids are, and then we have 4 really cold giant planets farther out. And we don't know whether that's something special enough to be necessary for our own existence. So, for instance, question: where does the water on the Earth come from? And in another solar system that's not shaped and made like ours, would there be water on the little rocky planets or not? So we're hoping to answer that question sometime soon.
Yep. Now this is a weird picture. What are we seeing here?
This is a result of a galaxy collision. The little red galaxy in the upper left corner went right through the middle of the lower hand of the one on the right.
Was that a spiral galaxy that it went through?
Yeah, it went through a spiral galaxy. So you're seeing the result of a splash. That bright ring around the right-hand galaxy, that's the material that splashed out of the center when the other little galaxy went through it.
How did the little galaxy stay intact?
Well, it's held together by gravity. The gravity is enough to hold it together, even that after it's been, in a way, attacked by an interloper.
Because we're expecting we're expecting in about 5 billion years that Andromeda, the nearest big galaxy to us, will actually collide with us. It will make a close pass in 2.5 billion years time, but it will actually collide in about 5 billion years. And we don't expect either galaxy to survive. We expect some kind of amalgam of the 2 galaxies to survive. It's been given the rather ridiculous name Milkomeda, But
Yeah, yes.
but in this particular case, it's amazing that the little galaxy has survived intact. With looks like it's got spiral arms.
Yeah. It's probably not really intact. I think what we're
Right.
seeing is the result of new stars being born in the gaseous material that was disturbed. So
And what would have happened to anyone, any intelligent civilization around a star in the big galaxy when that galaxy went through? I mean, there would have been a lot of disturbance, or would it have been
actually,
on long timescales?
actually, nothing would happen to that civilization except they would have a good time watching the show. Because stars are very, very far apart compared to the size of solar systems. So it was very rare for one star to disturb another.
Right, and yet the large-scale structure of that galaxy has been disturbed.
Yes. So yeah, when two galaxies come together at relatively slow speeds, they will scramble themselves together, and we'll get instead of a grand spiral, we'll get a sort of mishmash of mostly random orbits. On the other hand, this one was just different, as a head-on impact at high speed.
Now this is another gas cloud. I mean, again, are we seeing hot stars that are already formed at the top, blowing away this dust in the bottom of the picture?
Yeah, that's what we're seeing. This is another version of the process we saw in the Eagle Nebula and the Pillars of Creation. So yes, there are really bright new stars above, and you can see them in the picture. The stars are the ones with a hexagonal pattern of spikes sticking out of them, and that's just due to the diffraction of light on the hexagonal mirrors in our telescope. So anything with spikes sticking out of it's a star. And all of the rest of these things are different. Either they're faint so that we don't see those spikes, or they're fuzzy like dusty clouds, so then they don't have that. So we have hundreds and hundreds of new stars being born inside this one. Also, there are a few places where you can see a remarkable shape, and we're just beginning to zoom in on those remarkable shapes to say, well, what is that? So again, we see the effect of the wind blowing by. That's huge velocities of material flowing past little knots of dense material where a new star is being born. So there's a place in here where you can see there's a star that's sending out two jets of material, and one of the jets is being bent over by the wind. It's just right there in the sort of center left of the picture. So we can't magnify it enough for our audience to see it, but it's super interesting to magnify it and try to understand the forces on that object.
An interesting thing you said was that the six-pointed stars are an artifact of the telescope because it has hexagonal segments with six-fold symmetry, and that makes me think that if you were to get a Christmas card showing a biblical star, it would tend to have points, but presumably before the age of the telescope, nobody drew stars with points.
Yeah, I don't know what they saw in ancient times, but I do not see points on the stars with my eyes either. So
presumably if you see four, it's because the secondary mirror is being held by four Strauss above the primary mirror.
So it used to be we had four, now we have six. But before we had a telescope with a secondary mirror in it, we just had round things.
Yes. Yeah, so you know, we think of that as I don't know, an ancient biblical scene, but in fact it's actually a modern depiction of a star.
Yes. Yes.
And this is Stephan's quintet, which is in fact 5 galaxies, one of which is actually not associated. It's nearer or further or something like that. And this is showing them interacting in a way we've not seen before, isn't it?
Yes. So there are a lot of special things in here. The nearby one is the one on the left, and it is so close by that we can actually see individual stars in it, big red ones. The 4 on the right are in the process of merging with each other. You can see The sort of reddish orange sections are where new stars are being born today, just like in those other clouds we saw in the other pictures. And the top one is actually special in another way because it's got a black hole in the middle. Astronomers call it an active galactic nucleus. And so how can you see a black hole? Well, it means that stuff is falling in to the black hole, and it gets compressed and heated to immense temperatures on the way in. So it's hot and easy to see. And it's extremely compact, so it looks like a star, but it isn't. And so also this picture does show you jets of material come out from the black hole area. This is material that was orbiting around the black hole and couldn't get in, but got squeezed out instead towards the north and south poles of the system. So we see that there, and we've actually zoomed in with our spectroscopy to see, well, what are the chemical elements orbiting around the black hole? So, and what's going on? So we see numerous things. We see, of course, carbon and oxygen and other things like that, which are commonly produced in stars. We even see dust grains, which we call silicates, meaning they're like sand. And so that's interesting because that tells us there's even quite close to the black hole, there are places that are cold enough to make new stars. And that's interesting because now the new stars can fall into the black hole also. So it's a really complicated process in the middle of that galaxy. So
you make a really interesting point because the pioneers of the first people to be interested in black holes, like people like Robert Oppenheimer, they never guessed that the black holes would be bright. They assumed that they would be impossible to find because they would suck in matter and light. But of course, what we actually see is that many black holes are super bright because of the material as it swirls in. Friction heats it to millions of degrees, and these are some of the brightest objects in the universe.
Yeah, it's quite a lovely surprise.
Yeah, but we realize now that that's an active galaxy, but we thought that only 1% of galaxies were active galaxies, but that just means they're only active for 1% of their time. And our Milky Way itself, although it's got a rather small supermassive black hole, has been active in the past and may be active again in the future if it gets some fuel, some food, some sustenance.
Yes, well, it is getting some. Once in a while, a star falls in to the black hole in the middle of our own Milky Way, but there are not enough of them to make a big fuss right now. So we are very pleased when we can see one or two of them happening. So, but they're in there.
Are we having this conversation because our Milky Way has a relatively small supermassive black hole? Because when you look at the galaxies with black holes which are tens of billions of times the mass of the sun, they tend to have these tremendous jets of material that stab out through the galaxy, change the type of stars that can form. Could it be that we're here on Earth with made of the elements necessary for life because we have a small supermassive black hole, and that there may not be rocky planets and life in some of these more powerful active galaxies?
Yeah, that's quite possible. If the black hole in the middle of our galaxy was much more active, it would have sterilized the neighborhood. There's so much heat and light and high energy radiation coming out that it would have completely disrupted the formation of new planets and new stars. Even though we're way on the outer edge of our own Milky Way, we're about 10,000 light years. No, sorry, 10,000 parsecs, about 25,000 light years out from the center. It still would have bothered us.
So what can we expect from the James Webb now? I mean, what are you looking forward to the most?
Oh, well, we are definitely working on exoplanets right now. So we found out some years back that most stars have exoplanets. And so we've got a long catalog of places to look. So the way that we do it is we know when an exoplanet is going to go in front of its star, and we watch that happen. So this is not a discovery, this is an analysis. So what we do is we spread out the light of the star into a spectrum, the colors, and we say, well, does the planet have a color? Does it absorb more at one wavelength than another? And so some of the light of the star goes through the atmosphere of the planet on its way to our telescope. So we analyze that difference and say, maybe I see something that tells us there's an atmosphere out there on the planet, or there's not. So we don't have that answer directly, but we're observing the most promising targets as we speak. So we'll know.
Would that be the TRAPPIST system? Because I mean, that's a system with about 7 rocky planets, isn't it?
Yeah, it has 7 rocky planets, and our question right now is, do they have any atmosphere? And if we get lucky and some of them do, then we'll say, well, do they have any molecules in that atmosphere or anything else?
So we'd be specifically looking for oxygen and maybe methane, which we think are associated with life, would we?
We would love to find that, but we're not expecting to be able. The telescope was not designed for that, and so it can't see the best wavelengths for those molecules. We, on the other hand, are pretty sensitive to water. So we already know we can see water in exoplanet atmospheres by this method, but we just don't know if we can see it in little rocky planets around M stars, which are the little bitty stars that are easiest to study.
And how far are we away from ever being able to image a planet directly and create? I mean, presumably we would need a very, very large optical telescope to do that.
Yeah. Well, we already have some pictures of planets taken directly with the Hubble and even with the Webb.
But only a few pixels, is that true? Just a few pixels.
They're only big and bright planets, usually pretty hot and pretty young and pretty far from their stars. So nothing like Earth orbiting around the sun. So to get a picture of that, we need another telescope that's a lot more powerful than the Webb. Not necessarily bigger, but more powerful in a different way. It has to be more accurate so that we can see the little planet next to the glare of the bright star. So this, the sun is 10 billion times as bright as the Earth, as seen from a distance. So that's an awfully big difference. So it's like trying to see a firefly next to a searchlight, and we can't, not with what we have. But we know what we have to build. So we're thinking about how to do it.
I noticed that I think it was Abraham Loeb at Harvard was saying that the Webb should be able to see industrial chemicals, the fingerprint of industrial chemicals like fluorocarbons. Is that anything that you would expend any effort looking for?
Well, you would look, but it's the same search that you would do for the other molecules.
Yeah.
In other words, you just take your spectrum, spread it out, and see whether there's a sign of the different wavelengths that different molecules absorb. So water, carbon dioxide, carbon monoxide, methane, and freon. They all have their own spectra. So we wouldn't do a special experiment. We just do the same one and see what's in it.
And there is a planet around the nearest star. Proxima Centauri has.
Yeah, there is. So
is that going to be a target of James Webb?
Of course. I don't know when it is being observed, but yes, of course. Also, Alpha Centauri, which is at least got a chance to be like the sun. I mean, this Alpha Centauri is like the sun, but is on the other hand a double star. So it's not really like the sun either.
It's a triple system. So the nearest star system is a triple system. The sun is slightly unusual in being a solitary star when most stars appear to be double or triple. Yeah. So what about the unexpected? I mean, presumably you're hoping that something completely that nobody expected that this telescope will find. I mean, but when they built the Large Hadron Collider, they were specifically looking for the Higgs particle, and they found the Higgs particle. But a telescope is something different, isn't it? It's kind of open-ended. You don't know what you're going to find.
Yeah, and I think that's because basically astronomy is like biology. Complexity occurs spontaneously, if it can. And so basically that means we're not able to imagine what we're going to find before we find it. So every time you get a new tool, we see something that's different from what we knew about. So Well, I guess the surprise that I got, observationally speaking, is we're able to see individual stars at immense distances. Um, because of these lenses that nature gave us, the gravitational forces of clusters of galaxies, there are places where the magnification goes to unlimited high values. So over 1,000, over 10,000. So if you're just lucky and there's a star just lined up exactly on that place where the magnification is so high, then you can see an individual star. So this last week at our conference, we heard that when you do this, almost every time you look, you will find an individual star that magnifies so much. So I never imagined that. I knew we could try the experiment, but I never thought it would be so
Yeah.
easy. Not that it's easy, but it's so surprising that there are so many of them.
Right. So anyway, we're getting near the end now. How did you get interested in astronomy in the first place as a child?
Well, I think I was about 8 years old, maybe before. And I was reading, and my parents took me to the museum. I saw the planetarium show in New York City. And I was excited about the stars and also dinosaurs and volcanoes and other things that little kids are excited about. So I just wanted to know how everything worked. It was also about the year, maybe 1953, that Mars was coming very close, and people thought maybe this time we'll really see the canals, which don't exist. But everybody was very optimistic. So then I went through grade school thinking, well, the coolest thing is really relativity and quantum mechanics. So I got a chance to read about that and hear more about that in high school. Then in graduate school, I came back to astronomy through physics because I found a thesis project to measure the cosmic background radiation, the Big Bang radiation. And so that led me to here in a rather chaotic process.
When did you realize that you had an extremely unusual ability, and that was you're not just a front rank scientist, but you can motivate, coordinate large teams of people, you can deal with the politics of what's going on as well? There are very, very few people that can do this.
Yeah, well, you give me more talent than I have, actually. What we have actually is team structures, and there are people who specialize in all the pieces you mentioned. So I've been concentrating on the science part and maintaining the vision of why it's so important to do these things. And other people who are much better at it have figured out the politics and the engineering and the coordination of the project. So I'm not a project manager, I'm a project scientist. So to me, what the project manager does is more magic than what I do. And I'm just in awe of what they're able to do. They had to coordinate what turned out to be 20,000 people working on the Webb telescope.
Wow. So what next for you? 26 years on this telescope. Are you going to have a quiet retirement, or is there something else that you want to do?
Oh, absolutely not retiring. That would be so boring. So I have a wonderful teams of people to work with, and I have lots of ideas about new missions to work on. So number one, obviously the one that you already asked about, the telescope that would see the little Earth's orbiting sun-like stars, something like the Webb, only different. Also ideas for hybrid observatories. We have huge telescopes being built on the ground that are much bigger than what we can get up into space. And they could work better if we could put something in space to help them. So a couple of things that I've been working on. One is a laser beacon shining down on the telescope to help it focus better and get sharper images. And the other one is even more difficult. It's called an orbiting star shade. If you could put up a disk about 100 meters across, it could cast a shadow of a star onto the telescope on the ground. And calculation says if you could do this, you could see those little planets out there in a 1 minute exposure.
Right.
1 minute. So that's fast enough to be interesting.
Wow. Well, listen, on that point, thank you so much for your time. That's been absolutely fascinating. So great. Thank you again. And for everyone listening, tune in a month's time and we'll do this all again, and I'll have someone else fascinating to talk to. So thank you very much for joining us.
Thank you, Marcus. It was fun talking with you, and welcome to the audience. Please follow us online.
Thank you. Thanks.